I'm going to go ahead and raise what's on the board here. We did this yesterday. This was the review of the quiz. And in this, on the board right now, is probably 80% of what you need to know from the module. It's on the board right now. So you may not recognize it as such, but 80% of the module content that you need is on the board right now. Because not in terms of specific numbers, but in terms of the processes to use to solve these types of problems. What I'm going to do is go ahead and start working toward reviewing the module. And just so you're aware, if we were to consider what you turned in today for homework as your current ability, but not what you're going to be able to do when the exam comes, right? I know this weekend is homecoming, which means, and as I've been told by a couple of your parents, you have been looking forward to homecoming every year of your entire school experience. This is the culmination of all of your experiences, right?
No.
Does you guys all feel that way about homecoming, right?
No. Yeah, I'm excited.
Yeah, I'm excited too.
I'm excited.
There's a lot of different opinions about it, okay, and how much we invest in it. But anyway, even though this is homecoming weekend, and again, based upon the quizzes that you all turned in, I don't feel comfortable giving you an exam and then giving this super high curve so that only 2 people fail. I mean, that's not ultimately what I'm trying to do here. What I'm trying to do is for you guys to understand this material and how to do it. What I'd much prefer to do is spend the next 3 days walking through the problems and the type of problems. What you turned in for homework is going to count towards a grade, but it's not going to be your only graded events prior to the module exam. I'll tell you that. Okay? What we're going to do right now is go through the practice problems and the extra practice problems, and I want you to note the types of problems. There are only, I'll suggest to you, there are only 3 different kinds of stoichiometry problems that we're asked to do. And there's a few things we're asked to do with regard to empirical formulas. Some of the concepts in the module may be difficult at first for you to understand, but how to do the problems follows a standard pattern. And I've said it several times. If you understand the standard pattern, the standard flow on how to solve the problem, you're going to do fine with solving the problem. If you don't know how to, for example, use your calculator to enter scientific notation, those monkey skills, yes, you may have trouble on the exam. But there's no reason for you not to have a good understanding of at least the process to follow. Now, because I'm giving you a process to follow, you may not understand the concepts maybe as well as you should, which is where the review questions come in. Okay? But I would argue for stoichiometry, the types of problems we have, you should not lack for an understanding of the process you need to follow to solve them. So what I'd like you to do is follow along with me. I'm going to turn to the practice problems right now. Module 8 practice problems. And I just want to walk through the problems, take a look at the problems, and try to recognize the different types of problems that we're dealing with. Okay? So for example, practice problem number 1. You should be able to read that problem and recognize that it's a stoichiometry problem. What are we relating in practice problem number 1? It says when 21.3 moles of C3H8 burn in excess oxygen, how many moles of CO2 will be formed? So we have a reaction equation, right? Matter of fact, assume it's complete combustion means that you know that it's going to be this chain fuel plus O2 reacts to produce CO2 plus H2O because it's complete combustion. We learned that in the last module. So you could write the reaction equation. And then hopefully you know that once you write that down, you need to go back and balance the reaction equation so that you end up with a balanced reaction that describes the burning of this chain fuel, the combusting of this chain fuel producing carbon dioxide and water. Once you have the balanced reaction equation, now you can use stoichiometry. Remember, you cannot use stoichiometry until you have a balanced reaction equation. In this case, they didn't give you the equation. You had to write it yourself. So you better make sure to balance it. Now, in many cases, they'll give you a balanced reaction equation already, so you get to start from the second or third step. So, but this first type of a question right here, you can see that stoichiometry relating moles to moles. Okay? Relating moles to moles. So, moles relating to moles. And that's going to be, right now we've got practice problem number 1. What about practice problem number 2? We've got a reaction equation. You're given a certain amount of moles, and you're asked how many moles of another reactant or product. It's another moles to moles relationship using stoichiometry. Number 2. Okay. Number 3. Freon in this balanced reaction equation, if given a certain number of moles in excess reactant, how many moles will be formed? Question number 3 is a moles to moles relationship. Number 4, in the reaction of number 3, looking back to that same moles to moles, and it's using liters. Okay? Liters to liters. Number 4. Number 5, making phosphorus fertilizer. Balanced reaction equation, grams to grams. Number 6, phosgene. Balanced reaction equation, grams to grams. Number 7, magnesium hydroxide in a balanced reaction equation, grams to grams. Number 8, an empirical formula. Okay, we're going to move on to something that's kind of different. All of these up to this point have dealt with stoichiometry. I guess we could say stoichiometry proper. Okay? It's taking the balanced reaction equation and just doing math to relate things to other things. Now when we get into the empirical formula, we're actually looking at applications of stoichiometry. How could we actually use this sometimes in the lab? And so they're related, they are kind of the same thing, but they have a different feel to them, right? It's not so much of just looking at the balanced reaction equation. Now we're going to something that may have actually occurred in the laboratory. And how do we use stoichiometry with some practical, real-life kind of responses, real-life kind of answers? So number 8 is a compound has an empirical formula and a molar mass. What's its molecular formula? So the empirical, related to its molar mass, produces, and I tend to circle them to remember what I'm talking about, the empirical formula and its relationship to its molar mass, then what is its molecular formula? That's number 8. Number 9, an unknown compound in decomposition. Okay, so you've got a decomposition in grams. You have a decomposition in grams. What is its empirical? Producing an empirical formula. That's number 9. And number 10, a dry cleaning compound is decomposed into certain numbers of grams. That's going to allow us to get an empirical. And then it says a separate experiment gives us the molar mass. So the empirical related to the molar mass produces the molecular. So if you walk through the module and you then walk through the practice problems, you notice that we have stoichiometry proper with questions that either relate moles to moles, liters to liters, which uses which law? Gilles-Sachs. Okay, so moles to moles can be used with gases if you apply Gilles-Sachs law, and then grams to grams. And also the way that I've shown you on the board, hopefully you see that these are these two, from moles and grams, are just an extension of the process that I've already shown you. If you learn by doing moles to moles, that's the horizontal part of the diagram that I showed you. And then you learn how to go from grams to moles, and that's the vertical portion that I showed you on the solution diagram. Okay? So you start with moles to moles. That's core basic principle stoichiometry. And then you derive the moles by using molar masses moving from grams, and you find your solution in grams by going from moles using the molar mass to get grams. So answering this kind of problem here involves the concepts above it. So if you can solve this, you necessarily have to be able to solve these, right? Because this grams to grams includes these concepts plus a little bit more. This concept of moving from grams to grams includes the concept of moles to moles plus the additional concept of grams to moles by virtue of the molar mass. If you look at the empirical and molecular formula section of the module, the first step here, you see that it's empirical formula related somehow to its molar mass to give us a molecular formula. And here, given the decomposition of a molecule to give us the empirical. Oh, but look at here. Decomposition in grams to give us the empirical related to the molar mass to give us the molecular. What do we have here? These two concepts brought together in one. So in this case down here, this final type of problem is a combination of these two problems. If you can do this and you can do this, add them together, you can do this. And by virtue of that, if you can do this kind of a problem, you have to know how to do these two subproblems, these two subparts. And this is problem number 10. Didn't mark that on the board. So strategically, if you had to quickly go back and make sure that you understand all of the concepts for this module that are in the practice problems, or qualified that are in the practice problems. If you wanted to understand all of the concepts that are covered in the practice problems, knowing that the exam is heavily based upon the practice problems, and also knowing that the review questions cover the concepts, you would assume that if you can just nail the review questions and you can nail the practice problems, you are in good shape for the exam. Agreed? Okay. So if you can do the review questions and practice problems, you're in good shape. And if you can get problems 5, 6, and 7, and you can get problem 10, you're in good shape of getting all the practice problems because those include all the concepts that we've covered. So if you were to focus on understanding anything, hopefully you'd focus on understanding problems 5, 6, and 7, and number 10. Now, one other thing to note, for those of you that have been working on it already, is the extra practice problems. Remember, the extra practice problems are designed to help students with those areas that are particularly difficult and or are particularly heavily put on the exam. Or more accurately, they don't teach to the exam, but are crucial for you to understand in this module. It's crucial for you to understand those concepts, and that's why we do the EPPs as well. For those of you that have already worked on the EPPs, which I know is everybody. However, maybe you haven't. Maybe life has gotten in the way of your academic studies. I understand that. But for those of you that maybe have looked ahead, what do you notice about every single EPP? Pardon?
I'm guessing either stoichiometry.
They are, but they're a particular type. Stoichiometry is kind of like saying they're chemistry. Yeah, they are. This is whole modules on stoichiometry. So yes, it involves stoichiometry. But I'll give it to you. If you look at the extra practice problems, every single one of them, I feel really cautious about making that kind of a statement. But every one of them that involves stoichiometric proper questions is one of these questions. Every one of them is a grams to grams question. Okay? Every single extra practice problem that comes from that region I'm calling stoichiometry proper is a grams to grams question. Why would that be? Because if you can do grams to grams, you can do moles to moles and liters to liters. You have to accomplish this. And then at the bottom of the page, they include 4 questions on empirical formulas, and they include basically one of each of these types, again, but they do include this full-blown decomp to empirical related to molar mass gives you molecular. And those are the ones I'd focus on if I were you. Because if you can do those questions, you can do, theoretically, any question from that segment. Okay? All right. Let's go ahead then and walk through, which is a question just like yesterday's quiz. Just like yesterday's quiz. All the steps are exactly the same. But again, if you've been paying attention marginally up to this point, this is your opportunity to say, I understand how to walk through the process of a grams to grams stoichiometry proper question. And if I understand the process, I can now go back and apply that process to every single question. Not only that includes grams to grams, but includes moles to moles. And by extension, liters to liters. Okay. So, on problems 5, 6, and 7, which one of those would you like me to use as the example of how to solve a grams to grams stoichiometry proper question? I'm going to solve the problem, but I'm also going to write down the process of what we need to make sure we do in what kind of an order. Okay? Since grams to grams is the big question that covers all the concepts. So 5, 6, and 7, which one do you prefer? Any votes? Will says 6. Anybody else? Ma'am? 6? Okay, we've got a 7 in there. 6 and 7, 7, no, 6, 7, 7, 7, 7, 6. I'm not an auctioneer, I don't know how to do that. So, anybody else? Strong preferences? Let's go ahead and start with 6. Don't worry, we'll get a chance to do 5. Let's just start with 6 while we look at process, okay? Number 6. Phosgene, see it as COCl2, was once used as a chemical weapon in war. When humans breathe in the gas, it reacts with the water in their lungs in the following way. Okay. It's pretty horrific, by the way. Maybe picking number 6. People go, oh yeah, there's the retired Marine Corps officer choosing the warfare question. But no, that's not it. This is actually pretty gruesome. Look at it. Notice the formula, COCl2. Plus H2O reacts to produce CO2 and 2 hydrochloric. Okay. I know I usually ask you to picture what's happening in this reaction. So, you're breathing in phosgene, and when it reacts with water, now when you breathe in, where is it going to find water? Water in your lungs, water in the water vapor, right? You breathe. So H2O gas, you're breathing it all the time when you breathe in air because air has water vapor in it. So it's reacting with the air, the water vapor that's in the air, and the water that's in your linings of your lungs. Okay? And so when phosgene finds this water and reacts, it makes carbon dioxide, which you breathe out, but it also produces hydrochloric acid. So what you're breathing in is it's reacting with water vapor, and it's leaving behind hydrochloric acid in your lungs, which begins to burn your lungs. It destroys your lungs. You see in the next part of the question, the product HCl, hydrochloric acid, burns the lining in the lungs, making them unable to function. And when your lungs don't work, big surprise, you die. Okay? So by breathing in phosgene, a person will eventually suffocate. Now, we have the reaction equation. Okay? So step one, first we're going to do is write the reaction equation. Second, if the reaction equation was a decomposition, for example, and you have elemental products, go through and note the homonuclear diatomics. Might be a second step. Third, balance the equation. Now I'm going to assume that they gave us a balanced reaction equation, but I'm going to check it real quick. Okay? 1 carbon, 1 carbon. 2 oxygens, 2 oxygens. 2 chlorines, 2 chlorines. 2 hydrogens, 2 hydrogens. I've already accounted for the oxygen. It's balanced. Now that I know that it's balanced, now I can use stoichiometry. Until I know it's balanced, I can't use stoichiometry. I can't relate something to something else in an unbalanced equation. But now that I have a balanced reaction equation, I have the perfect recipe. Now I can say, this and this reacts to produce this and this in these proportions. Okay? Going back to the problem. Assuming that 5 grams of hydrochloric acid in the lungs is deadly. Okay? So I'm given a number, I'm given a mass, 5 grams of hydrochloric acid. Now the technique that I've encouraged you to do with the balanced reaction equation is to do what next? Now that I've been given 5 grams of hydrochloric, right? I'm going to write what I've been given from the problem in terms of mass. I'm going to write it directly below the molecule. A little bit to the right to save room underneath the stoichiometric coefficient. But I've been given 5.00 grams. Okay. We're going to assume that 5.00 grams of hydrochloric acid is deadly. So how many grams of phosgene would a person need to breathe in order for them to die? Again, kind of a morbid question, but it's a chemistry problem too. People get paid a lot of money to sit down and figure this stuff out. Okay? At least they're using chemicals, and they're not creating little bugs that go and do the work for us, right? It's not a bioagent, it's a chemical agent. Bad, but I've got opinions on that too. Phosgene says how many grams does a person need to breathe? How many grams of phosgene are necessary to react in order to produce 5 grams of hydrochloric acid? So, reaction equation, made sure my homonuclear diatomics, if I wrote the reaction equation on my own, are accounted for. Balanced the equation, wrote down the given and the unknown, and now I just need to move in a legitimate way from my given to my unknown. The process I taught you was to go ahead and draw a vertical line below the stoichiometric coefficients of the 2 molecules in question and connect them with a line. That reminds me, as I look at this balanced reaction equation, that I'm relating the phosgene and the hydrochloric acid. That keeps me centered, keeps me with my reference points, right? I always encourage you, too, to write down your known and your unknown, because what's going to happen is, if you just write down your given of 5 grams, and you forget what you're supposed to solve for, you could stop at this point and get an answer which is true but not correct. You might give me an answer on the exam that's in moles, and that might be true, but it didn't ask for moles, it asked for grams. So write down the given, write down the unknown that you're asked for, and then what you're doing here by drawing this line is you're giving yourself a solution path. If you walk the path from your given to your unknown and do each step along the path correctly, you will get the right answer. That's my promise to you. So you need to be able to figure out what the path is and then take each step along the way. Now, generically speaking, we now have a path, and there are certain parts of this path that I can fill in because they apply to every single question, no matter what it is, right? Certain parts of the common process. I know, for example, I'd like to put arrows to say that I'm moving in this direction, I'm moving in this direction, and I'm moving in this direction. We've learned now that the key of moving between masses and moles, over here, I can write moles of HCl. These are grams of HCl. I can write over here moles of phosgene. And then this is how many grams of phosgene, right? It's going to be moles are in the corners, and the molecule is going to be the molecule in question. Applies every time. Another easy thing to remember is as I move from grams to moles, and I move vertically down in my process, it involves a mathematical process, right? A mathematical function. What is, or an operation? What is the operation moving down? It's division. Vertically down is division. So I'm going to just note over here that this is division. And the inverse is moving up, and the inverse mathematical process is multiplication. So this is going to be a process of multiplication on that side. I also know that whatever I'm looking for to go from moles to mass or mass to moles involves a standard piece of information in every problem like this. And that's the molar mass. I might use MM, let's say. The molar mass is going to equal something. The molar mass of what? The molar mass of the molecule or element in question. On this vertical, the element or molecule in question is phosgene. So here, it's going to be the molar mass of phosgene. That's what I need to know. On this side, the molar mass of the molecule in question is hydrochloric acid. So what is the molar mass of hydrochloric acid? And what is the molar mass of phosgene? Two pieces of information I'm going to need to know. I can't move from here to here without going through this step. I can't go from here to here without going through another step, which we haven't noted yet. And what is that?
Multiplication.
Right, the molar relationship, the relationship between the stoichiometric coefficients. The relationship here, I can always just go ahead and put my relationship symbol, the colon, look over here and say, what is my stoichiometric coefficient of the molecule in question?
1.
It's an implied 1. And on the other side, it is a 2. I am moving in this direction, and by process, you've learned that as you're moving and you have your relationship, the first number you hit is driven into the denominator. And so my multiple becomes 1/2. Right? So I need you to check me because I'm doing this with you, okay?
Yes, you do.
Okay, 1/2. Now what does 1 relate to? It's 1 mole so 1 mole of COCl2 relates to 2 moles of hydrochloric acid, right? This is 1 mole of phosgene relates to 2 moles of hydrochloric acid. Is that right? My units don't appear to be right. What are we messing up?
What did you multiply?
Okay, no, we're fine. We're good. I'm looking at it the opposite direction. We're fine. Let's just keep doing the process. Just doing process. Because I was reading it from left to right, but our actual process is going to be from right to left, and that's what's messing me up. So let me go ahead and box this up. Okay? I derive this multiple from this stoichiometric relationship. Okay? And that's going to be true. See, just give you insight where I was messing up, is I was reading it from left to right, and I was saying, wait a minute, I'm going to have moles of COCl2 squared over, but we're not going to multiply this by this. We're going to multiply this by this. And you can see that moles and moles cancel and leave the appropriate units. So we're good. So everything that's generic that I know is up there now. I could do all of this without looking at any other source. I only need 2 pieces of information. And then I can just start using my calculator and going to town and solving it. The 2 pieces of information I need are the molar masses. The molar mass of hydrochloric acid and the molar mass of phosgene. How am I going to do that? Go to the periodic table and look up the mass in AMUs of every element that makes up the molecule and multiply that by the number of times it occurs in the molecule to find the molar mass of the whole molecule. For example, hydrochloric acid, its molecular formula is HCl. I have 1 hydrogen and 1 chlorine. Chlorine has a molar mass 35.5, and hydrogen has 1.01. We normally round that to 1.0. So 36.5 is the mass of the molecule, correct? 36.5. 36.5 AMU per molecule, which is also equal to 36.5 grams per mole. And we need it in grams per mole because those are the units we're dealing with. Yes?
Does that 2 not apply to
The 2 does not apply. You're looking for the molar mass of 1 molecule. Stoichiometric coefficient comes into play here, not in the molar mass of the molecule. We're not saying what mass of this do we get in the balanced reaction. We're just saying what is the molar mass of one of those. Okay? So molar mass of hydrochloric acid is 36.5 grams per mole. And we do the division, grams divided by grams per mole. Just real quickly here, you've got grams divided by grams per mole. Hopefully you recognize that that is the same thing as saying grams times moles per gram. Grams cancels grams and leaves us with moles. Okay, so the units work. Grams divided by grams per mole, the units are moles. So, without a whiz-bang calculator, somebody help me out. How many moles of hydrochloric acid do we have? 5 divided by 36.5.
137.
0.137 moles of hydrochloric acid. Okay. So, my molar mass of hydrochloric acid for one, remember you're computing the molar mass, that's 1 molecule is AMUs per molecule, and then you, by extension, make that grams per mole. Well, disregard, at this step, disregard the stoichiometric coefficient. You're just getting the molar mass of 1 mole of the molecule. 36.5 grams per mole. So another way of saying 5 grams of hydrochloric acid, 5 grams of hydrochloric acid is equal to 0.137 moles of hydrochloric acid. It's 2 ways of saying the same thing. But we translate it from the language of grams into the language of moles by using the molar mass. Right? Now, we are here. Our next step is to get to this corner. And we do that by passing through the operation of multiplication. And as I said before, if you look at it as this times this, it'll help if we look at the multiplication sign on that side to check our units. The moles of hydrochloric cancels moles of hydrochloric and leaves us with moles of phosgene. So we have 1/2 of whatever this is, 0.137. Half of that is 0.06566, something like that, right? What'd you get there, Ray?
0.0685.
0.685. Okay, let's run with that. 0.0865 moles of phosgene. Right. Now we can go back in there and say, over here we had 3 significant and 3 significant and 3 significant. So over here we have 3 significant. 0.069. Okay. Technically that's more accurate. because this is going to be exact number, which means it does not affect significant figures. Okay, so whatever the sig figs here were, 3 divided by 3, the least sig figs is 3, multiplied by an exact number means sig figs are 3. Okay, and so we're at this step here. So remember, this is saying this in a different language, from grams to moles. This is relating based upon the balanced reaction equation, moles to moles. So whenever this many moles, we can now say, we can answer the question, if the question were, given 5 grams of hydrochloric acid, how many moles of phosgene would have been breathed? And you could come back and say 0.069 moles. The next step is to go from moles to grams. So we do that again through the molar mass. In this case, the molar mass of phosgene. We've got carbon, which is 12, oxygen, which is 16, which gives us 28, and 2 chlorines, which give us 71. Right? So what do we have there for the molar mass? 71, 12 and 18, or 12 and 16, 28, 71, 98, 99. So this is 99 grams per mole. When I multiply this by 99, it'll give me how many grams of phosgene. It's basically 100, so I'd expect it to be like 0.69. Right? Pardon? I would say, did somebody get an answer?
6.83.
6.8. 6.8 something? What? 6.8, we need one more sig fig.
3.
6.83. Okay?
Let me double check.
So, I trust you. That's good. It's closer than some of you could measure on the triple beam balance, okay? It's within range of your error. So, right here you have the process, everything you need to do a moles to moles. This is the first type of problem. The second type of problem was liters to liters, which you would, again, you would do the same exact way. Rather than moles, you put liters, with the condition that you only analyze gases. And then the third type is gram to gram, which we walk through the entire process here.